And we're back to talk about Snell's Law. So in lab, we investigated the relationship between the angle of incidence and the angle of refraction. So the angle of incidence, of course, is this angle right here. It's the angle at which the incoming ray of light is measured from the normal. And then the angle of refraction was the angle down here, the angle at which the refracted ray of light is traveling with respect to the normal. And so in lab, you plotted on the x-axis the sine of the incoming angle, and on the y-axis the sine of the refracted angle, and you got a linear relationship. So we would say that the sine of the refracted angle is proportional to the sine of the incident angle. And your slope here is probably different than mine, but that's kind of the basic idea. So we're going to be using some sines, and so let's just do a quick little review here. You might remember that if you have a right triangle, then we can call this angle theta, and then this is the adjacent side, this is the opposite side, and of course this is the hypotenuse. And the sine, cosine, and tangent are just ratios of the sides. So if you take the length of the opposite side and you divide it by the length of the hypotenuse, you get the sine of the angle. And your calculator has these built in. So you can grab your calculator and just make sure this works. Try taking the sine of 30, and I think when you do that, you should get 0.5. If you don't, you're probably not in degrees mode. So switch your calculator to degrees mode. If you take the sine of 65, you should get, the sine of 65, you should get about 0.906. So those are pretty straightforward. And of course, the sine of 23 degrees, you would get 0.39. So that's fairly straightforward. So if I had a 30-degree triangle, if this angle was 30 degrees, then whatever the opposite side was, when I divide that by the hypotenuse, I'm going to get 0.5 because the sine of 30 is 0.5. Okay? All right. Here's the problem. What happens if I don't know the angle, but I know its sine is 0.8? How do I find the angle? Well, you could guess and check. You could take the sine of 30 and the sine of 40 and the sine of 50 and keep guessing and checking. But there's an easier way, and you may or may not have had this in mathematics, and that's okay. If you want to find the angle theta, and what you're looking for is inside the sine, you have to use the inverse function. We call this the inverse sine or the arc sine. So if the sine of an angle gives you a ratio, then the arc sine or the inverse sine of the ratio will give you the angle. So if the sine of theta is 0.8, then theta is the arc sine of 0.8. And arc sine is sometimes written ARC sine, and sometimes it's written like this, a sign with a little -1. And you can usually get it on your calculator by hitting the shift button before the sign. So if you take the arc sine of 0.8, go ahead and try it and see what happens. You should get 53.13 degrees. Again, you've got to make sure you're in degrees mode. And then you're going to take the arc sine of 0.8. So hit shift sign and then put in 0.8, and that should give you 53.13 degrees. Let's just practice one more. If the sine of an angle is 0.626, how do we find the angle? Well, we have to take the arc sine of 0.626. Putting that in our calculator, we get 38.76 degrees. And you can check it. If you would go back here and take the sine of 38.76, you'll get 0.626. So we're going to use that because we're going to look at Snell's law, which involves sines. So here's kind of what we did in lab. We had an incoming ray of light. Its angle is measured from the normal. Here's an interface, so you can imagine this top up here is air and maybe it's water down here. There's some change in the optical material so that the light either speeds up or slows down. And in this case, it slows down and it's refracted at angle theta 2. So Snell's law tells us that n1 times the sine of theta 1, so n1 times the sine of theta 1 is equal to n2 times the sine of theta 2. So to help us figure out what this means, the left side of our equation deals with the incident ray. If you take the index of refraction of whatever it's traveling in, times the sine of the angle the incident angle, you will get a quantity that is the exact same for the refracted ray. If you take N2 of the refracted material times the sine of theta 2, you'll get the same thing as this left-hand side. So this is what we call Snell's law. Now, to connect this to lab, in lab, what you guys did was you actually, theta 2 is the refracted angle, so you plotted the sine of theta 2, the sine of the refracted angle on the y-axis. On the x-axis, you plotted the sine of the incident angle, and you got a constant slope. So if you want to check, you could go back, calculate N1 divided by N2 for your lab, and see if that's the same as your slope. It should be. So this equation is the exact same as Snell's law up here, just written in a different form, and this is what we discovered in lab. So if we were in class, we would have actually done this with laser beams and little blocks of glass, but we did a simulation since we're stuck at home. But we got the same result, and that's called Snell's law. So let's solve an example problem. Suppose light is traveling in air, and it strikes a body of water. So when light strikes water, it slows down. The angle of incidence is 30 degrees, and I want to know at what angle will the beam of light be refracted. All right, so the first thing I do, I got to figure out what is the light traveling in initially, and the answer is it's in air. So we have to find the index of refraction of air. Now you'll have this table available to you on all the homeworks, so you just got to look up what you're interested in. And so air is 1.00. We're only going to use 3 significant figures, so to 3 significant figures, air is 1.00. Okay, then the light strikes a body of water, so we've got to find water, and so that's right here in the table. And so the index of refraction for the N2 is going to be 1.333. So our problem is going to look like this. This is the same problem without the table. We're going to draw a little diagram. This is the incident ray. This is the refracted ray. We know it's originally traveling in air, so N1 is going to be 1. And we know that the angle of incidence was 30 degrees. We know it then passes into water, where N2 is 1.333, which we looked up in the table. And we're trying to find theta 2. What angle will this be refracted at? So we're just going to solve Snell's law. Here's Snell's law, N1 sine theta 1 equals N2 sine theta 2. And we're solving that for theta 2. We're trying to find out this thing right here. So to find that, I'm going to divide both sides by N2. If I divide both sides by N2, I'm left with sine of theta 2, that's here, equals this mess divided by N2. So I have N1 sine of theta 1 over N2. Now, that's not theta 2. That's the sine of theta 2. So like we just talked about with trig, if I want to find theta 2, the sine of theta 2 is this mess right here. So I've got to take the arc sine of that big mess in order to find theta 2. So the easiest thing to do is go ahead and calculate what's inside here. Take 1, that's N1, so that's 1 times the sine of 30 divided by N2, which is 1.33. And once you find that number, take the arc sine of that number, and if you're in degrees mode in your calculator, you should end up with 22.0 degrees. So that means that an incoming ray of light at 30 degrees was refracted at 22 degrees. So the angle of refraction is smaller than the angle of incidence. Okay, so that's how we solve the problem. Now, a quick note, which way does it bend? If the ray of light passes into a more optically dense material, that is, one where it slows down, it bends towards the normal. So here comes a ray of light, and if this ray of light passes into a material where it slows down, it bends towards the normal. See, this is the normal right here. This dotted line is where it would have gone if it didn't get bent. And so the actual path of the light is closer to the normal. So we say it bends towards the normal if it goes into a material where it slows down. But if it goes into a material where it speeds up, it bends the opposite way. So the beam of light going like this will actually bend away from the normal. Here's the path where it would have gone without a change in the speed. And so the angle of refraction ends up being bigger than the angle of incidence when it goes into a region where it moves faster. And it moves faster if n is smaller, because remember n is the slowdown factor. Okay, so let's just do one more example before we turn you loose. Here we have light traveling in a piece of plastic, and I do not know what kind of plastic it is. It refracts into a piece of glass where n is 1.333, and if the angle of incidence is 42 degrees, and the angle of refraction is 57 degrees, I want to know what is the index of refraction of the plastic. All right, so here's a diagram. Here's my beam of light coming along at 42 degrees, and it's refracted at a bigger angle, 57 degrees. So that tells us that the light must have been going faster in N2. Okay? All right. So we're trying to find the index refraction of the plastic, and so the plastic is N1. All right, so let's make a little variable list. We do not know N1. We know theta 1. We know N2. When it's refracted into the glass where N is 1.33, and we know the angle of refraction. So what we're going to do is we're actually going to solve Snell's law for N1. So here's Snell's law, and we're going to solve it for N1. So there's my plan. To get N1 by itself, we simply divide both sides by sine of theta 1. And so N1 is N2 sine theta 2 over sine of theta 1. Since we're not trying to find something inside of the sine, we don't need to use the arc sine. We can just evaluate this on our calculator. So you're going to take N2, 1.33, times sine of 57.5, divide by the sine of theta 1, which is 42 degrees, plug that all in your calculator, and you get 1.68. So the index of the refraction of the unknown plastic is 1.68. Okay? So that's how we solve problems using Snell's law. Okay, so now it's your turn, because it's just not a whole lot of fun to watch physics. It's more fun to do it. So you get to solve some problems now involving Snell's law.